chemical bonds. Is it or is it not polar molecules? When we look at covalent bond, we have to make a determination whether or not a molecule is polar or nonpolar. One of the things we can determine that it is nonpolar is that all compounds that have only nonpolar bonds are nonpolar molecules. However, not all compounds with polar bonds are polar molecules. Nonpolar molecules. As we stated before, any molecules with only nonpolar bonds are considered as nonpolar molecules. However, sometimes molecules with polar bonds can be nonpolar molecules. These are molecules that has no positive or negative sides, therefore no dipoles. They tend to be symmetrical. In regard to polar molecules, these are molecules that have positive and negative sides, so they have dipoles, and these molecules are asymmetrical. Now, what causes a molecule to be polar? One is the asymmetrical shape, and they tend to be like bent shape, trigonometrical, pyramidal, and so forth. We go on about that in a little bit more. And that's normally because there are unshared electrons on the central atoms. We'll take a look at some of the shape in a little while. So what drives these polarity molecules are the dipole moments that exist. So let's take a look at some of these shapes. So if you are bent or pyramidal, those molecules are always polar, and they'll always be asymmetrical. However, if the shape is tetrahedral, linear, or trigonal planar, it can be polar or it can be nonpolar. It depends upon the symmetry of the shape. So let's take a look at carbon dioxide. Now, carbon dioxide has a linear shape. That means it has 180 degrees between one side versus the other. When you write carbon dioxide out as a Lewis dot structure, you write it as follows. So you write carbon dioxide like this. So you can see that the shape is linear. More importantly, if you calculate and look at the electronegativity will be going away from the center. So the electronegativity value for carbon is 2.6, while for oxygen is 3.4, which means that the dipole moment is facing toward oxygen. And that way, the repulsion is minimized, therefore creating a linear geometric shape. So therefore, making carbon dioxide a fairly symmetrical molecule, thereby making it nonpolar. The next example is also a linear type of relationship in which we have hydrogen chloride here, which is hydrochloric acid. And if we draw this out, we see that hydrogen and chloride will have this type of relationship in which chlorine will have a higher electronegativity value than hydrogen. Hydrogen will have an electronegativity value of 2.2, while chlorine will have an electronegativity value of 3.2. So even though this is a fairly linear type of molecule, the electrons charges are centered around chlorine more than it is around hydrogen. So therefore, this is not an even distribution. As a result, even though it has a linear geometry, this type of molecule is actually polar because the dipole moment is actually going toward chlorine. The next type of shape that we are looking at is called bent. In bent, we're going to take a look at water, which is a very common type of molecule. In water, we have oxygen being surrounded by hydrogen, and oxygen has two additional pair of electrons that surrounds it. So we know that oxygen, it has a electronegativity value of 3.4, while hydrogen has an electronegativity value of 2.2. So if we were to draw out this arrow dipole moment, we'll see that the dipole moment actually goes this way. Now, under normal circumstances, you say, oh, that's very similar to the one that we've seen earlier before for carbon dioxide. However, because of the electrons, there are lone electrons here that are sitting on the central atom, which is oxygen, it repels, and the lone electrons actually has a stronger electronegativity than the one that is shared between oxygen and hydrogen, thereby resulting in the oxygen shape to be bent. So realistically, oxygen and hydrogen should look like this, with the two lone pair of electrons for oxygen pushing the bonded side toward the other side, so thereby creating a bent shape instead of a straight shape. So that's why we call this a bent shape and not a linear shape, due to the unpaired electrons that's sitting in the central atom. Now, one thing to note here is that anytime we have unpaired valence electrons sitting on the central atom, we tend to have a polar molecule. In this example, we have a trigonoplanar geometric shape, and let's take BF3 as an example. So I'm going to write B in the middle to represent boron, and F out here. Now we all know that F has the highest electronegativity value of 4. So therefore the dipole moment is drawn in such a way to show that the dipole moment is going toward F. And since there is no lone pair of valence electrons around B, this makes the compound a nonpolar molecule. Now, in this situation, we have a very similar one to the one that we just discussed. However, there is some slight difference. So again, I'm going to use NH3 in an example. So N goes in the middle, and H goes on the 3 outside. Now, however, there is a lone pair of electrons still outside here, and we can see that right here. And so as a result, remember that anytime there's a lone pair in the picture, this will make the molecule a polar molecule. Now, this is an example of a tetrahedral shape, because in this case, we have one central atom, which is C, for example, and we have 4 H's surrounding it, making it a tetrahedral shape. And since there is no lone valence electron in the middle, this creates a symmetrical shape, and so this is a nonpolar molecule. Now, in this example, we have a tetrahedral shape, as you can see. However, in this case, we actually have the outside 3 being H. However, the fourth outside element is not H, but Cl instead. So therefore, even though this is a tetrahedral shape, the electronegativity are not the same. So let's take a look. The electronegativity of H is 2.2, while the electronegativity of chlorine is 3.2. So therefore, chlorine is going to have a stronger repulsion, resulting in an asymmetrical shape. So that is why this particular molecule is a polar molecule. So to summarize, we saw a lot of different shapes. And we know that if you have non-polar bond only, the molecule is going to be a non-polar. However, when we have a polar molecule, we have to look at what type of shape it has. Now, if one rule that we can always look at is that if there are any lone pair of electron located in the central atom, this will make the molecule polar. The other thing we can consider is even though there is no lone pair of electrons in the middle, if any of the elements that surround the central elements is not of the same electronegativity value, this will also cause the compound to be a polar molecule. So again, think about the shape and think about how the lone pair or the electronegativity value can affect the geometric shape of a molecule.